right, this is the 1104 Electrostatics CFU from class on Friday, and I wanted to go over this just question by question until we get through it, because you guys have a test over this material, and I just want to make sure that we get any questions answered that still exist so that you don't miss those on your test. Question 1 says, object A has a charge of 105,000 coulombs and object B has a charge of -2 × 10 to the 13th coulombs. Which statement best describes the electrostatic forces acting on these objects? So when you take a look at this question, the charges on these objects are vastly different. They're both large, but -2 × 10 to the 13th is significantly larger than 105,000. And so we have very vastly different amounts of charge. I do know these objects are going to attract because they have opposite charges. One is positive, one is negative, but that's not really the question that's being asked here. It's just asking us how the forces compare. And what you need to remember is that it doesn't matter which one has more charge or less charge. This will be a force pair because both of these objects are experiencing the same electric field due to these charges. And so you're going to have equal and opposite forces. This is Newton's third law. We saw the same thing when we talked about the universal law of gravitation, and we looked at the force of gravity acting on objects that had very small masses versus very large masses, and it was an interaction between those two objects, just like any other interaction. It's just that now it's due to a field, but it's still going to come in pairs. It's still, Newton's third law still holds true. For every action there's an equal and opposite reaction. All right, question 2. Question 2 says a positively charged glass rod with a +4 nanocoulomb charge touches a piece of metal with a charge of -2 nanocoulombs. What is the final charge state of the metal? So here we're dealing with charging by conduction, where we have two objects that are touching one another. And when that happens, your charges will transfer until you reach electrostatic equilibrium. That just means that the charges redistribute themselves until everything has the same charge. So for example, if you had touched this positively charged rod to something neutral, let's say that it was +4 touching something neutral, well, that's a little bit easier of a problem, because you would take that +4 charge and you would split it in half, and then both objects would have a +2 charge afterward. And so that would be if it touched something that had a neutral charge, but we don't have that here. In this particular problem, we're dealing with opposite charges, and so what you have to do to approach this is you have to figure out what the total charge state is for the system. And so we had a +4 charge and we had a -2 charge, and that total charge for the system is therefore +2. And so instead of splitting this between them, okay, this is the amount overall charge of the system that gets split, and we're splitting it between the two objects. So that means both of them would have to have a +1 charge. So that should be 1 nanocoulomb. Question 3. As Mr. Guthrie runs a plastic comb through his hair, the comb acquires a negative electric charge. This charge results from the transfer of. Again, when you read these choices, you need to keep in mind that transfer of charge is due to the movement of electrons. Protons do not move. And so when we're looking at how objects obtain a charge, it's either because they gain electrons or they lose electrons. And in this case, we're dealing with a charging by friction scenario where you're going to have one of the objects losing electrons and the other one gaining them. And so these electrons are going to be either transferring from the comb to his hair or from his hair to the comb. And the clue here is that it tells us that the comb becomes negatively charged. So if the comb is negatively charged, that means that the comb has gained electrons. That's how something becomes negatively charged, which means that his hair has to have lost electrons. And so electrons would be transferring from his hair to the comb, and that's the answer that we are going to select here. It's the first one. And so again, you just need to remember, when you have a charging by friction scenario, that you're going to end up with objects at the end that have equal and opposite charges. So let's say that it was 50 electrons that transferred, then his hair would have lost 50 electrons and they would have been gained by the comb. The comb would have therefore a charge that is now -50, and his hair would have a charge of +50, for example. And again, you're going to transfer way more than 50 electrons. It's a tiny number. Anyway, this is how you're going to approach those charging by friction problems. Question 4 shows an electric field diagram, and it says, consider the electric field lines shown below for a configuration of two charges. Several locations are labeled on the diagram. Rank these in order of electric field strength from smallest to largest. Again, the strength of your electric field is determined by the density of your field lines. And so where you have the least dense field lines is where you're going to have the smallest or weakest electric field. And so you're looking for the spots where the lines are farthest apart. That's going to be definitely at point D. 100% that is where you have the lines farthest apart. And then from there, you're looking for where they are getting basically gradually closer together until we get to this side where they're closest. So after D, the next would be A, because the farther away you move from these charges, the farther apart the lines get. Except for over here where they are kind of coming together between the two objects. So that's why I said A would be next. And then we would have E. And then we would have, after that, these two are kind of tricky, B and C. It's difficult to tell because your field is strongest around the charges, except for this right here, they look pretty close too. And so you'll actually notice that I keyed it so that it takes either one. So I'm going to go ahead and put B here and then C here, but if you did it the other way around, it should also count that correct. This one says, based on the electric field diagram shown, which shows the correct free body diagram illustrating the electric forces on the two charges Q1 and Q2. Well, looking at this diagram, these charges are both positive, so I know they're going to repel, but I can also tell that by looking at the shape of the field lines. These are obviously repelling one another, so when I pick my free body diagram, I need to pick something that shows that the forces are pushing them apart, where they're moving away from each other, which means it's going to be one of these on the right-hand side. The question is, are those forces equal and opposite to each other, or do they have different magnitudes? And that is always going to be this one. Even if these didn't show the exact same amount of charge, because these look pretty similar, but let's say one of them had twice as many lines around it, it still wouldn't matter. We're still going to say that this is a force pair, just like we talked about in the first question. All right, this is question 5. It says, each diagram below shows two pith balls, which are foam balls coated with aluminum hanging from strings. A pith ball can be given a negative or positive charge. Which of the following diagrams shows a possible correct interaction for pith balls based on the charges shown in each diagram? So when I look at my options here, my first diagram shows two positive charges, and it shows them repelling, and that's exactly what would happen. If I had two like charges, they should absolutely repel. This would be a correct depiction because those pith balls could be positive or negative. It's just asking which of these is possible. So like if I look at this one, for example, these two negative charges, those should also repel. So I wouldn't want to select this diagram because two negative or like charges should repel. It should look like the first diagram, regardless of what the charge is. So I'm not going to select this or this for that matter, which leaves me with this one here, which shows opposite charges repelling. If I have opposite charges, they need to attract. They should be together like this. If this was a plus and a minus, I'd pick it. It's not. And this shows them repelling, which we don't want to pick either. So there appears to only be one correct answer to this question. Question 6. The diagram above shows electric field lines in an isolated region of space containing two small charged spheres, Y and Z. Which of the following statements is true? The two charged spheres repel each other. Well, not based on this diagram. This diagram appears to show attraction between them, so we're not going to select that. The strength of the electric field is the same everywhere. Again, remember, electric field strength is going to be determined by the density of the field lines, and these field lines are not the same everywhere. They are farther apart in some areas and closer together in others, and so we do not have the same electric field everywhere. The charge on Z is negative. Again, we talked about the way to draw these field lines. They always point away from positive charges and toward negative ones, which does mean that the charge on Z is, in fact, a negative charge because the arrowheads are pointing toward it. So we're not going to say that it's positive. The next one says both charged spheres carry the same sign. Obviously, that's not true. This shows opposites attracting, and I can tell that because, well, the arrowheads are pointing away from one and toward the other, so I know they're opposite. And I can tell that by the shape of the diagram. This diagram is literally showing them attracting one another. So I know that these guys don't have the same sign, they have opposite signs. And so we're just going to select the one that we've already picked. And there you go. Question 7. Two charges exert a force of 4 newtons on each other when separated by 2 meters. What would the force be when the magnitude of both charges are doubled? This is going to bring us back to Coulomb's law. So Coulomb's law is the equation that allows us to calculate the magnitude of the electric force or electrostatic force using this equation, where we have our constant K, our 2 charges Q1 and Q2, and we are dividing by the distance of separation squared. So that's the formula. And so the question is asking, hey, what happens if both of these are, the charges of both are doubled? So if I double both of these, well, if I double one charge, it's going to double this because they're directly proportional to each other. If I double both of them, then it's 2 times 2, which means it's going to be 4 times the amount of force between them. So if I double both the charges, I'm going to get 4 times the original force. It doesn't actually ask for the factor. I'm not putting in 4 times as much, but rather I'm looking back up at the question. I'm seeing the initial amount of force was 4, and so 4 times that would be 16. Question 8. According to Coulomb's law, what is the force object A is experiencing due to the presence of object B if they are separated by 2.4 meters? Again, this is also Coulomb's law. So first things first, yes, we're going to do the calculation, but before we do that, you'll notice that part of the question just asks us to pick the direction of the force. And so let's go ahead and do that part first, and then we'll deal with the calculation afterward, because we don't need math to answer this question. To answer this question, all we need to remember is opposites attract and like charges repel. When I look at my diagram here, I am dealing with 2 like charges, and so these 2 like charges should repel one another. The question specifically is asking what the force object A is experiencing. So object A is this object here. The force it experiences would therefore, since they're repelling, push it away from B, which means it should push it to the right. So that's the direction. Now we just have to do the math to figure out the magnitude. So if I go back to my equation here, we're solving for force. So K is the constant. It has a value of 8.99 times 10 to the 9th. And that's how I'm going to type it in my calculator. And then I'm going to multiply by my 2 charges, which are 4.8 and 5. I am not going to bring a sign with these. Now, these are both positive, but since this is randomized, some of you might have negative signs on one of your charges, or on both. Don't write them. We're just solving for the magnitude of force, so we don't want to carry that sign over here into the calculation because these 2 are experiencing forces in opposite directions. So the sign doesn't mean anything here. It would only be giving us one of them, so we just want to solve for the magnitude. And then the distance of separation is 2.4 meters, and that value needs to be squared. So that is my setup. So now we're going to get our calculator out, and we are going to type this in. So I have 8.99 E9 times 4.8 times 5, and then all of that divided by 2.4 squared. And I get this right here, 3.7458333 times 10 to the 10th. And that should be what we see right there, 3.458333 times 10 to the 10th, and of course it'll be in newtons. I think it is going to allow me, maybe I can, no, it won't let me copy paste. I have to type this one in. You actually can't use the E because of the way that it's programmed in. That should be enough digits, I think. Newtons. Oop. I just pushed the wrong button. Not trying to do that. Awesome. Okay, let me get out of all this. I don't know what just happened there. All right, back up here. There we go. Okay. Next one. Question 9. Two charged coins are 5 meters apart from each other. The $1 coin has a charge of positive 5.7 times 10 to the negative fourth coulombs and is attracted to the 1 pound coin with a force of 32 newtons. Determine the charge of the 1 pound coin. This is going to be another calculation involving Coulomb's law, but this time we're solving for the amount of charge of one of the objects instead of the force between them, because they actually gave us the force. 32 newtons equals my constant 8.99 times 10 to the 9th multiplied by my charges. I only have one of them because I'm trying to solve for the other, 5.7 times 10 to the negative fourth, and then I have Q2, which is what we're solving for. And then all of this is over the distance between them squared, which is going to be 5 squared. So again, if I want to solve for this, let's start by multiplying 32 times 5 squared, which of course 5 squared is 25. So 32 times 25 will be our first step. And then we need to divide by both of these values. So divided by 8.99 E9. And we're going to divide again by 5.7 E negative 4. And that should be our answer, 1.56118888. It has more digits. Let's see. Times 10 to the negative fourth. So this one is actually not in scientific notation. It's just in standard form. But this is times 10 to the negative fourth. You can see those 4 right there. The other thing you'll notice is my calculator doesn't give me this negative sign. However, if you look at the question, it says that this one has a positive charge and it says that they are attracted to each other, which means they do need to have opposite charges. So although the calculator doesn't tell me that, you need to go in and you need to add that negative sign in front of it in this case. And again, this is randomized, so not everybody's is negative. So I'm going to go ahead and type it in the way that it is on my screen. If you want to type it in scientific notation instead, you can. But it tells me that I need at least 3 significant figures, which is that one, if you're doing scientific notation, it's 1.56 E negative 4, or if you're doing it this way, you need the 1, the 5, and the 6 before you submit. It does need to be rounded right, so just make sure. All right, question 10. An object that becomes grounded gains neutrons during the grounding process. Grounding is a neutralizing process. It does cause things to become electrically neutral. It causes the discharge of excess electrons, or if they're lacking electrons, it causes objects to gain electrons, but it's all about the transfer of electrons in order to reach that electrostatic equilibrium with the ground. So it has nothing to do with gaining or losing neutrons. In fact, those can't move, and they don't carry a charge anyway, but they can't move. They're locked up in the nucleus. And so we're going to say that this is false, and then move on to number 11. Which of the following explains how a negatively charged balloon sticks to a neutral wall? We saw this in a PhET simulation. On the first day of simulations before spring break, there was one where you rubbed a balloon on a sweater and then stuck it to a wall. We also saw it in the notes slideshow on Thursday, where a boy had a balloon rubbed on his hair and it stuck to the wall. And in both cases, what was happening was polarization of the atoms that make up the wall. Now, the wall isn't a conductor. It's an insulator. It's a brick or, plaster or whatever. And so it doesn't have the free flow of electrons, but it does cause the distortion of the electron cloud. And it causes this temporary polarization due to the cloud being skewed, in this case, away from the negatively charged balloon, so that you have more positive charges on the surface of the wall. And so that's what this says. The balloon pushes the wall's negative charges away from the wall surface, resulting in positive charges on the surface that attract the negative balloon. Again, don't pick anything that talks about transferring protons, and you're not going to talk about transferring electrons either, because you're dealing with insulators here. Charging by conduction requires conductors. At least one of them needs to be a conductor in order for that to happen. All right. Question 12, what happens when a positively charged rod touches a neutral metal sphere? This is again charging by conduction. If you have a positive rod touch something neutral, kind of like we talked about at the beginning, you'd have, let's say, positive 6 charge touches something neutral. Well, then your charge is going to split between the two until you have that electrostatic equilibrium. That object that initially had a positive 6 charge is going to end up with a positive 3 charge by gaining 3 electrons. And the object that was neutral ends up losing 3 electrons, which is how it obtains its positive charge. Again, you're going to have things transfer from one object to the other until everything reaches equilibrium. So let's look at our options. Again, we're not going to pick anything that says protons move. We know that electrons are what moves, and for my positively charged rod, it's actually going to attract electrons. Opposites attract. And so that positively charged rod is going to steal electrons from that neutral metal sphere. So electrons move from the sphere to the rod is what we're looking for, which is actually the last option here. And then afterward, both of these things are going to be positively charged. Again, if we started with positive 6, it'd be 3 and 3, but they would both have the same charge, and they would both, in this case, be positive. Question 13. An electrostatic force exists between 2 charged particles. Each particle has a charge of negative 8.01 times 10 to the negative 19th coulombs, and they're separated by a distance of 0.06 meters. As the distance between the 2 point charges is increased, the electrostatic force of fill in the blank. This is going back here. Again, we're looking at this equation, and we're talking about what happens as that value increases, the distance between them. So first things first, we need to figure out if this is attraction or repulsion, because when you look at the choices, that's the first part of the answer. And it tells us that the 2 charged particles have the same charge. Each particle has a charge of negative 8.01. So they're like charges, they will repel. So I know I'm picking one of the ones that says repulsion. And we're talking about this distance getting bigger. As this number gets larger, that means we're dividing by a larger number, and it gives us a smaller amount of force. And so we'd say that the repulsion between the 2 charges decreases. We're going to get a smaller amount of force as the objects are moved farther apart from one another. And they are still repelling because they have like charges. All right, question 14. A student performs the following steps using a negatively charged rod, 2 metal spheres that are initially neutral in step 1 shown below. And it says, what is the charge on sphere L in step 4? Guys, this is charging by induction. That's what it is. You have these 2 objects that start out neutral and they're touching. You bring a charged object nearby without touching it. That causes polarization. When this negative rod comes nearby, the electrons that were evenly distributed between these 2 are going to flow as far away from this rod as they can. Like charges repel. And so the electrons are going to be more concentrated in sphere R, and because of that, that means sphere L will have lost some of its electrons, leaving sphere L with a positive charge, but it's not permanent until you separate them. And so that's what's happened here by step 4, is that sphere L ends up with a positive charge because the electrons were repelled by the rod. They went into R. R became negative, L became positive. All right, last one involves a triboelectric series and a question about charging by friction. It says, suppose we have a sample of steel that we want to give a positive charge by friction. Using the triboelectric series provided above, select all materials that we could use. So steel, first of all, is right here. And you need to be able to read the chart. So the objects that are higher up on the chart tend to lose electrons, which means that those objects tend to become positively charged, which is what we want to happen to the steel. In order for steel to become positively charged, it has to be rubbed against something lower on the list, because these objects down here tend to gain electrons, meaning they would take away electrons from the steel and leave the steel with a positive charge, and these objects down here would be negative. If you did it the other way around, you're not going to get the right charge on your steel. To get a positively charged sample of steel, it needs to be rubbed against something lower on the list. Again, these are randomized, so yours might not be asking the same thing. So read it carefully. But I can rub the steel with wood, rubber, plastic wrap, or Teflon. I see wood and Teflon. If I rubbed steel with cat fur, for example, the cat fur would be the one that loses electrons. It would be positive. The steel would be negative. Okay, so that's how you read this chart. If we want to make it positive, it has to be rubbed with something that is below it on the list. All right, guys, that is it for the CFU that you took in class, and these questions are very similar to what you should expect to see on the multiple choice section of your test. Obviously, your test will also have free response, and so you just need to keep in mind the main tenets here, which is it's only the electrons that move. opposites attract and like charges repel. If you can remember those rules, then that should be enough to get you through any written explanation as well as the multiple choice section. All right, guys, so make sure that you're studying. Use the unit summary if you're looking for extra practice, or go back through your past problem sets to help you prepare for your test.